Hello, Chem 213 students, and welcome back for our second lecture of this week. When we finished in the last lecture, we were talking about substitution reactions of benzene, the molecule benzene alone, and we ended with the so-called Friedel-Crafts acylation, in which a acyl group here, an acylium ion as it's called, when it reacts here with the AlCl3, this acylium ion right here, behaved as a nucleophile and underwent a nucleophilic attack here from the benzene ring, producing a sigma complex, and thus ultimately producing a substitution with the acyl group. And of all these electrophilic substitution reactions, aromatic substitution reactions that we saw so far, these occur through the formation of a sigma complex intermediate and then a recovery of energy by the restoring the aromatic ring, which recovered all of the energy required to get to this sigma complex in the first place. In all of these cases, we are doing a substitution with a hydrogen atom on a benzene ring. And what we're going to start to look at now is the way in which these substitution reactions differ when you already have a substituent on the benzene ring. So two issues arise when you're adding a group to a ring which already possesses one or more substituents. We're going to start by considering trying to do the nitration of a toluene group. So we have to consider two main effects here. One, what is the effect of the group itself in terms of the presence of the electrons in the ring? Is it going to donate electron density to the ring, or is it going to pull electron density away from the ring? In the case of a carbon atom does not have a strong electronegativity. It's the same as the other carbon atom, and it can donate electron density through the hyperconjugation effect that we have learned earlier, in which essentially the sp2 hybrid orbitals here in the sp3 here can kind of interchange hydrogens in order to share electron density. So the CH3 group here is electron donating, which makes the ring a better nucleophile. But the second issue is also important, and that is the effect of the methyl group on the regioselectivity of the reaction. Because we have a methyl group here, if we have a carbocation that ultimately lies in this position, it will be a tertiary carbocation, which will provide significant stability to the intermediate, and thus will have a great effect on the regioselectivity of the addition reaction, because any addition that will result in a resonance structure that leaves a tertiary carbocation, that will be significantly more stable as an intermediate, and thus will lead to a faster reaction, producing the ultimate product. So in terms of this nitro addition, so we've seen this nitro addition before, it's going to occur by a similar mechanism. However, the difference here is we have this installed group. So the question is, it's going to add NO2. We know that from the last lecture, but where is it going to add NO2? Is it going to add at the ortho position, or is it going to add at the meta position, or is it going to add at the para position? And so that's the question here. And to analyze what will occur, we should think about the potential intermediates that may be produced during this reaction. So what we observe experimentally is that when we do this nitro addition to toluene, we get the most significant addition at the ortho position. At 63% of the molecules produced will have the nitro group installed at the ortho position. The second highest installation, the second highest product here that will be produced, the second or the most significant isomer here that will be produced, is the isomer that installs the nitro group at the para position at 34%. And what we'll see is that we get almost no nitro group installation at the meta position. So in order to explain these results, we have to think about the intermediate that will be produced during this reaction. So we have to consider the mechanism. And that is why it is so important for you to understand that mechanism from the last lecture that goes through that sigma intermediate, the so-called sigma complex intermediate. So, well, we should consider the three potential situations in which the nucleophilic attack can occur from the benzene ring to the this nitronium ion here. And so when this occurs, if it occurs at the ortho position, we'll have a nucleophilic attack. We'll have the nitro group attached at the ortho position. And that leaves a positive formal charge here because this carbon had 4 bonds and no lone pairs. Now it has 3 bonds and no lone pairs. So it has a positive formal charge. And of course, we have the same sigma complex intermediate. And so we have the associated resonance structures. But note that one of these resonance forms has a positive formal charge at the tertiary carbon, which is significantly more stable and adds extra stability to this. In fact, that tertiary carbocation is produced immediately at the ortho position upon the nucleophilic attack of this NO2 plus ion. Now, when the nucleophilic attack occurs at the meta position, we end up with the nitro group here at the meta position, and then at the para position, we have the carbocation intermediate. And note that in all of the resonance structures here, so we have a allylic carbocation, so we move the arrow here, we have pi bond shown here. Now this carbon is shown with 3 bonds, no lone pairs. Again, we have a allylic carbocation, so we have this resonance arrow. And now notice that the positive formal charge never lies on the tertiary position. And so this means that none of this resonance structures will not be nearly as stable as the ones that allow for a tertiary carbocation as a part of the resonance structure. Now, if an attack occurs at the para position, here the nitro group will be installed at the para position. At the meta position, that will be the carbocation. And if we draw our resonance arrows here for the allylic carbocation, that will result in this carbon here having 3 bonds and no lone pairs, and thus being positively formal charged. So we can see that both the ortho attack and the para attack involve these sigma complexes that have a tertiary carbocation as a part of the intermediate, and therefore additional stability. So that explains why we see preferential installation of the nitro group at the ortho and the para position, particularly the ortho position. So in terms of the intermediates here, we can see that our intermediate is going to be significantly lower in energy, and so is the transition state that leads to that intermediate. So we're going to get a significantly faster reaction to produce that intermediate, as opposed to the meta attack, which is going to have a much higher energy intermediate and thus a greater activation energy barrier. That's really going to slow down this meta attack. And then at the para attack, we're going to have also a lower activation energy to get to that intermediate because of its lower energy here. So we can see here that the meta attack is going to be kinetically unfavorable versus the ortho or the para attack. So the ortho and the para products will predominate and will get almost none of the meta product. And so we say that this reaction is going to be ortho-para directed. And it's going to produce the ortho and para products significantly more than the meta products. So in addition to the methyl group here being electron donating to the ring, the methoxy group will also be significantly electron donating to the ring. In fact, it will be even more electron donating to the ring because unlike the methyl group, it has resonance forms that spread that electron density out across the ring very effectively. And that can be demonstrated by these resonance structures here. We have this arrow representing a allylic lone pair here, Of course, this carbon cannot have 5 bonds, so we have to show these electrons here as residing on this carbon, producing a carbanion. Then we have another allylic lone pair, and so we have this double arrow here moving this one, another allylic lone pair, and then finally we have another allylic lone pair, which then gets us a 5th resonance structure. So we can see that we can actually directly see the electron donation through resonance, not just through hyperconjugation. And so this is a significantly greater donation of electron density to this ring, making it an even better nucleophile. Now, the methoxy group activates the ring so strongly that often you don't even need the Lewis acid catalyst, such as AlBr3. In the case of the bromination, we can simply use bromine if we have, without any other catalyst, if we have a methoxy group. Unfortunately, we're going to get significant halogenation like this at both the ortho and the para direction. These activators, the methyl group and the methoxy group, are going to be called ortho-para directors, which means they promote substitution at the ortho and para positions relative to those. So like the methyl group, the methoxy group is activating and is thus an ortho-para director. And again, we see that we have significant preference for installation of a nitro group, let's say in the case of nitric acid and sulfuric acid, at the ortho and para positions rather than the meta positions. Now you can see that in terms of the relative amounts of the ortho and the para, in the case of the methoxy, which is a little bit larger group, you do have some steric hindrance for the nucleophilic attack at the ortho position compared to if you just had a methyl group, due to its larger size. And so we get a preference towards the installation of the nitro group at the para position rather than the ortho position, as we saw with toluene. So we have a ortho and para direction here for this reaction for the same reasons that we had it for the methyl group as a substituent. If we have an ortho attack here, again, the nitrogen here being the nucleophile, we get the positive formal charge, and this is at a tertiary position here. But in addition, we have a couple of different resonance structures here. We have allylic carbocation, but also we have allylic lone pair here, but this carbon cannot have 5 bonds, so given the way it's drawn, we've got to move these here. So now we have the positive formal charge here on the oxygen. And we can see that this is resonantly stabilized throughout this whole area here, whereas if we have a meta attack, we don't have that same resonance stabilization. Here we have allylic carbocation here, and then that leaves this one here as a carbocation, allylic carbocation, but then the carbocation is here. The carbocation never lies at this position here. I think the easier way to see this is just to show, like, oh, here we have carbocation adjacent to a lone pair, and then that will take us, if we do it that way, that will take us right over here, which is a little bit easier way to see that, I'd say. But we can see that that is not possible here. We never have the carbocation in the position of the carbon right next to the oxygen with the meta attack. However, we do with the para attack. So we have a para attack position. Here we have the now the carbocation at the meta position. We have an allylic carbocation. That puts the carbocation right here at the carbon next to the oxygen. Now we have a lone pair adjacent to a carbocation. We can do that. And that brings us right over here to this structure. We also have another resonance structure where we have allylic carbocation right here. And so neither, the meta attack does not involve the formation of this additionally stabilized intermediate. And so that, for that reason, the methoxy group is also an ortho-para director. A little bit different than the methyl group, but pretty analogous. And we can see again, we have significant resonance due to the significant resonance stabilization. We have, for the ortho and the para attack, much lower energy intermediates, thus also having much lower energy transition states, thus having lower activation energy, whereas we don't have that kind of stabilization for meta attacks, or activation energy very large, thus slowing down the meta substitution significantly. Besides activating groups, there are also deactivating groups. So activating groups make the benzene ring a better nucleophile by donating electron density to the benzene ring. Deactivating groups make it a worse electrophile by taking electron density away from the aromatic ring. And one of the most important deactivating groups is the nitro group. Once you install a nitro group, you heavily deactivate the ring, and this is due to the fact that, first of all, the nitrogen is electronegative along with the oxygen atoms, so you get a significant inductive effect withdrawing electron density. But also, you have resonance in which electron density can also be removed from the benzene ring, resulting in a carbocation on the benzene ring rather than a carbanion. So you saw with the methoxy group here, before we had any reaction, we saw with the methoxy group that the resonance structures, you could see the donation of the electron density due to the resonance structure showing a negative formal charge within the benzene ring, that additional electron. However, with the nitro group, you get the opposite effect. You get a positive formal charge in the resonance structures due to the fact that here we have a positive formal charge adjacent, or an allylic positive formal charge. So we have this arrow. Of course, nitrogen cannot make 5 bonds. So we have to draw another arrow. This arrow is a pi electrons between 2 atoms of differing electronegativity, putting the electron density there in the oxygen. That leads to a resonance structure in which we have negative formal charges in the oxygen. The nitrogen is making 4 bonds with no lone pairs, so it's missing an electron. It would usually be 3 bonds and 1 lone pair. So it has a positive formal charge. And now we can see the result is that this carbon now is making 3 bonds with no lone pairs. So it has a positive formal charge, and we have resonance all the way around the ring here. But what we can see is this whole situation is withdrawing electron density from the ring and putting it on these highly electronegative oxygens, thus making the ring less negative and thus a worse nucleophile, because the best nucleophiles are negative, right? And so it can't donate that electron density as easily to an electrophile. So nitrobenzene is going to undergo nitration 100,000 times slower than benzene. In addition, it's going to have meta direction rather than ortho direction. So what we can see is that if we do if we try to install a nitro group here on a benzene ring that already contains one, it's going to heavily favor the installation of the nitro group at the meta position, and it's also going to be much, much slower than it would be because of that deactivation of the ring. So why is it that this installation of the meta position is preferred rather than ortho and para? Well, it's going to be the same reasoning behind the last one. It's going to be due to the resonance stabilization of the carbocation intermediate that occurs during the nucleophilic attack. So we have the nucleophilic attack here of the benzene ring on the nitrogen. Again, not so great because electron density is being pulled away from the ring by the nitro group. But that's going to lead us, though, to a tertiary carbocation, which is relatively stable, stabilized here. However, note that when we look at this, let's take a look at the resonance structures. This is a nitrogen atom. That's a little bit different, right? Before we had tertiary with 3 carbon atoms, but this is a nitrogen atom. That nitrogen atom is highly electronegative. So it wants to pull electron density away from this carbon, but this carbon is lacking electron density. That is a less stable situation. And so we can see now that, of course, we have allylic carbocation, so we have multiple structures, but this structure is actually less stabilized than the one where we had a tertiary carbocation, because the carbon here is not electron donating to this positive formal charge carbon. Instead, it's having electron density pulled away even further making it even less stable. But we have the meta attack here. Notice what happens. We have the positive formal charge here can occur either at the para or the para or the ortho position. But either way, we have a allylic carbocation giving us a couple of resonance structures here. And none of these have the positive formal charge on the nitrogen. They don't have that highly unstable situation here. In addition, with the para attack, we have the installation of the nitro group here. We get at the meta positions a carbocation. And now we have an allylic carbocation, and that leads to a resonance structure in which the carbocation is positioned on the carbon attached to the nitrogen. Again, this nitrogen wants to pull electron density away, but this carbon is already lacking in electron density. So that's a particularly unstable situation. And so our intermediates here are far less stable on the para and the ortho attack. These intermediates are much more stable, particularly because they don't have these resonance structures here with the positive formal charge attached to the nitro on the carbon attached to the nitrogen. So we can see here that we have the opposite situation. In all cases, the activation energy is kind of high, but we can see that the activation for the activation for the meta attack is much lower because it produces a much more stable carbocation intermediate versus the ortho and the para attack, which produce this carbocation intermediate that has a positive formal charge on the carbon attached to the nitrogen. So as we've seen, all of these electron donating groups are ortho-para directors. All electron withdrawing groups are meta directors, but a exception here is going to be with halogens. Okay, so we just saw an electron withdrawing group, the nitro group, which is meta director, but with a halogen atom, it will not be a meta director. And let's talk about why. The halogens are withdrawing the electrons by induction to deactivate the ring. They're pulling the electron density away just simply due to their electronegativity. But halogens do donate electrons through resonance, which helps them to be ortho-para directing. Let's take a look at why that is. So first of all, so we have two competing effects here in this case, unlike the nitro group, where the effects were not competing. It was deactivating, and it was also through resonance withdrawing electron density. Here it's deactivating by induction, but it's actually donating electron density through resonance. So here we have an allylic lone pair, and so we can have the formation of this pi bond. And if we need a second arrow here so that we avoid having 5 bonds, and we have the lone pair here. And then we have allylic lone pair, allylic lone pair, allylic lone pair, and we recover the 5th resonance structure here. So we have two competing effects here. So the halogen groups are not going to be nearly as deactivating as the nitro group, but they will still be deactivating. But the difference is, instead of being meta directing, they will be ortho-para directing. And here is why. So if you have a electrophile here that, like this NO2 plus ion here, that is reacting with the substituted benzene, if you have an ortho attack here, you're going to put a positive formal charge here next to the chlorine. However, we can see here that now we have this situation, and again, it's probably easier to just take a look and say, well, this lone pair is adjacent to a positive formal charge. That's one of our resonance patterns. And this would produce for us a situation where the chlorine has 2 bonds and 2 lone pairs, and thus is bearing the positive formal charge. And so in this case, we have a stabilization of this ortho attack through an additional resonance structure that does not exist for the meta attack. And so we can see here too, there's allylic lone pair, allylic carbocation. So we have some other resonance structures here too. But this is the additional resonance structure that does not exist when we have a meta attack. We have a meta attack, we get a positive formal charge either at the para position or at the ortho position. Either way, when we look at all the resonance structures here, we have lone pair adjacent to carbocation here, allylic carbocation rather. And so we move that here. Now here's the three bonds, no lone pairs carbon. We have allylic carbocation. Here again, we have the third resonance structure. But in no cases do we have the opportunity, like we had here with the positive formal charge next to the chlorine, to make this other resonance structure. However, if we have a para attack, then our carbocation will be at the meta position. And here we have an allylic carbocation, which puts our carbocation here at the same carbon as the chlorine. And now we can do this situation where we have lone pair adjacent to a positive formal charge, and we get this additional resonance structure that occurs, further stabilizing the intermediate. So let's now think about which kinds of groups are going to activate the ring, which are going to deactivate the ring. Remember, in general, activators are going to be those groups that can donate electron density to the ring. These include alcohols, for example. We have allylic lone pair here, so we can get this situation, and this is going to produce for us a carbanion here at this position, and that's going to be donating electron density to this ring. Likewise, we have, again, allylic lone pair here with a the benzoxy radical here. That's going to, again, donate electron density as a lone pair here, carbanion on this carbon. Likewise, again, allylic lone pair here, we can donate electron density. Allylic lone pair, we can donate electron density. Allylic lone pair, we can donate electron density, right? Now, so all of these are strong activators by donating electron density to the ring through resonance. Although they do withdraw electron density by induction, the resonance is more important here. Now, acyl groups and amide groups here, these are going to be moderate activators because they can donate electron density due to allylic lone pair, but they don't donate it completely because they're also allylic to this group right here, the carbonyl group. So not only do they donate electron density to the ring, but they have to donate it out here outside the ring too, which reduces their effectiveness as activators. That's true here for this lone pair of electrons as well. This one right here, same thing. And then in this case, what's going on is that we have for the if we have a carbon group here, this is pulling electron density a little bit itself. Not as bad as these, but it's different than a hydrogen atom, which cannot pull electron density at all. A carbon atom will significantly more than a hydrogen atom will. And so an alkoxy substituent is only a moderate activator, not a very strong activator like these other groups here. Finally, weak activators are alkyl groups, methyl, ethyl, isopropyl, and any other alkyl groups. These, again, donate electrons not through resonance, but through hyperconjugation, which activates the ring slightly. And of course, these are all ortho-para-directing, all of the activators. For deactivating groups, the nitro group we already covered, which withdraws. This is a very strong deactivator because it withdraws electron density not only through induction by these very electronegative atoms, but also through resonance, both. If we have a protonated nitrogen here or a nitrogen with 4 bonds, this is going to have a positive formal charge. And of course, here we have now a allylic positive formal charge. This is going to pull electron density away from the ring inductively and also by resonance. Finally, if we have halogen atoms that are not directly, they're not aryl, but they're benzyl halogen atoms on the carbon attached to the benzene ring, these will be strong deactivators as well, and they will all be meta-directing. So when the halogen atom is not directly attached to the ring, it's meta-directing. Moderate activators, those are going to be those that can withdraw electron density from the ring somewhat. These include, and these would be by resonance as well. So here we can have, a pi bond between 2 atoms of differing electronegativity, which would end up giving us a carbocation here. And then we'd have an allylic carbocation. And so this is going to be true for all these carbonyl groups. Any carbonyl that is benzyl is going to be deactivating. Also, these sulfonyl groups and cyanide groups will also be deactivating for the same way, and they will be meta-directing well for the same reasons as with the nitro group. Finally, weak deactivators include halogen atoms, but these are ortho-para-directing, which makes them different because unlike these other groups here, which are all withdrawing density at least partially through resonance, these are only withdrawing electron density through induction. And so in these cases, you have the ortho and para directing that we discussed by this previous mechanism there. The halides are the only deactivating groups that are ortho-para directors. This is important, right? And you should remember why this is as well, as we discussed in the mechanism. So what if we have not just one substituent already on the benzene ring? What if we have two or more substituents? What will happen then? Well, the directing effects of all the substituents must be considered for the electrophilic aromatic substitution reaction. The directing effects of methyl and nitro let's say, so methyl group is an activating group, which is ortho and para directing. The nitro group is a deactivating group, which is meta-directing. If these are directing both to the same position, well, then that's going to extra support the installation of the group at that position. So we have, in this case here, we have a methyl group which activates the ring and is an ortho-para director. So you're going to want substituents here installing it. It's going to prefer installing at the ortho position. It can install at the para because it's already a nitro group. The nitro group is deactivating, but it's a meta-director. It's going to promote installation of a group here and here. So if we do a halogenation with the iron 3 bromide catalyst, that's going to exclusively go to this position here, while this is an equivalent position, because both groups are directing the installation at this position. Ortho for the methyl and meta for the nitro. But what if the groups are not directing to the same position, right? So if the groups direct to different carbons, whichever is the stronger group will direct the effects. So for an alcohol group here, the phenol is going to be a strong director, and it's going to be ortho-para. Remember, it's a strong director due to the fact that it can donate the electrons here as an allylic lone pair to the ring in resonance structures. The methyl group is a weak ortho-para director. So these are both going to promote the substitution, but they're going to promote it at different positions. Since the OH group here is the stronger director, it's going to direct it to the ortho positions. The methyl group is also an ortho-para director, can install a para because the OH's group there is here. But it will also want to go to its ortho positions. But since the OH group is the stronger director, if we do an installation of a nitro group, for example, this is going to go ortho to the OH. One thing to consider is if we have an alkyl group or a methoxy group or any large group, we have to consider the steric hindrance when we have the nucleophilic attack. So for example, if we have this monosubstituted ring here with the isopropyl group, this is going to be electron donating. It's going to be activating the ring. However, it is also an ortho-para director, so it's going to want to install a group here at the ortho positions or at the para positions. So if we do the installation of a nitro group with nitric acid and sulfuric acid, it can install at both the ortho and the para positions. However, the para position is going to be preferred because due to the isobutyl group here, the nucleophilic attack is going to be a little bit sterically hindered at the ortho positions, which are right next to it. So we're going to have a minor product of the installation of the NO2 groups at the ortho positions, but a major product here at the para positions due to the lack of steric hindrance. If we have this, as an intermediate, whoops, I should put it over here. We have this guy undergoing nucleophilic attack. It's going to be much more blocked off right here because this is going to be getting in the way than a attack that occurs right here instead, which has no steric hindrance at all. Steric hindrance must be considered when more than one product is possible. For 1,4-disubstitute rings like this one here, we can see that the isopropyl group here is going to have significantly more steric hindrance than the methyl group. So, again, these are both activators to the ring. They donate their electrons by the hyperconjugation from carbon. And they're both going to be ortho-para directors. So they're going to, the isopropyl group here will be ortho director, promoting the installation of the group right next to it, and the methyl group will as well. So the deciding factor is going to be the steric hindrance. And again, nucleophilic attack from the ortho position to the isobutyl will be sterically hindered due to the large isobutyl group here. It will be much less hindered here at the ortho positions for the methyl. So our major product is going to have the installation of the group, in this case a nitro group, ortho to the smaller, less sterically hindered methyl group, rather than the larger, more sterically hindered region here by the isopropyl group. So the major product will be ortho to the methyl group. Steric hindrance must be considered again when more than one product is possible here. Here's another example. Here now, the isopropyl group and the methyl group are meta to one another, which produces a different situation. So again, these are both ortho-para directors. So the isopropyl group here is going to be directing for the installation of, in this case, a nitro group at the ortho or the para positions. Now the para position is open. The methyl group is going to be supporting the promoting the installation of the group at the ortho or the para positions, but notice that the para position is sterically hindered due to the isopropyl group. So the only one that's least sterically hindered and promoted by both is this area right here, because it is ortho to the methyl group, but it's para to the isopropyl group, and it's less sterically hindered than this position here, which is ortho to the isopropyl group, para to the methyl group. So the major product will have the installation of the nitro group ortho to the methyl group, para to the isobutyl group. You'll also have installation ortho to the isobutyl group and para to the methyl group, but it will be much more sterically hindered due to the presence of the isopropyl group here, so you'll have a minor product there. And you won't get any installation of the nitro group ortho to both, because there will be significant steric hindrance due to the isopropyl group and the methyl group together. So let's start to think about how we can direct where the group is going to be installed. Because having a group on here providing steric hindrance can make it difficult to attach a group to a position that is ortho to it. What if we want to put for example, let's say we have this isobutyl benzene here, and we want to install a group at the ortho position. Well, this is significantly sterically hindered. So how is it that we're going to make this happen? What we want to do is we want to make it so that we cannot install at the preferred para position. So remember, this is ortho-para directed, so these are the three positions where it can be installed. But we want the bromine to be installed here and not here. And so what we can do is we can put something there that will block the installation of our group at that position, and then remove it afterwards. And this is referred to as a blocking group. We install a blocking group, then we can halogenate in the normal way. Again, we'd halogenate with Br2 and, like, for example, AlBr3 or FeBr3. And then we can remove the blocking group. So what can we use for a blocking group? Well, ideally, we want something that's very reversible, and we learned about a reversible installation of a group, the sulfonyl group. If we use concentrated fuming sulfuric acid, we can install the sulfonyl group, but then if we expose it to dilute sulfuric acid, we can remove that sulfonyl group. So the synthesis would work like this. We'd start by reaction with fuming sulfuric acid, which would preferentially add the sulfonate group to the para position due to the fact that the ortho positions are very sterically hindered. Then when we do the halogenation, then at that point the only possibilities are installation at the ortho position. And so installation at the ortho position occurs. Then we treat with dilute sulfuric acid to undo the sulfonation. And then we have the product. So this is the way, if we're trying to do a synthesis and we need to install at the ortho position, this is the way we would do it. We would install a sulfonyl blocking group with fuming sulfuric acid and remove it with dilute sulfuric acid. So that is it for the electrophilic aromatic substitution for benzene rings that are already substituted. When we come back, we're going to be talking about additional reactions. We're going to be talking about synthesis considerations when we do these substitution reactions. We're going to move on and talk about two more types of reactions, including nucleophilic aromatic substitution instead of electrophilic aromatic substitution, and also so-called elimination addition reactions. So I look forward to seeing you in the next video, which will start on section 18.12. Textbook.